So as we begin today, we're going to look at some connections that we can make from delta G to both K and E, and then do some more delta G and general thermodynamic practice. Looking up here, there are two equations that you will need to know. And by know, I actually mean know how to use, because both of those equations are on the AP equation sheet, so do not memorize them. The first one is connecting delta G to K. So this is something that you can probably figure out. It's pretty intuitive, but if delta G is negative, we know that the reaction is spontaneous or thermodynamically favored in the forward direction. That means K needs to be greater than 1, and products need to be favored for forward to be favored. All right? So if delta G is negative, K has to be greater than 1. So the reverse is true. Non-thermodynamically favored reactions would have K's less than 1 because the reverse reaction would be favored. So if delta G is positive, K is less than 1. And when you do the math with that, it's consistent. So you'll be able to think about your answer before you actually calculate. Now the other one is delta G connecting to E. We have not done E yet. E is going to be at the very end of the year when we do electrochemistry, but what E stands for is volts. It's our electric potential in volts. And just a really quick thing, a really quick synopsis. Volts, like 9-volt batteries, when we have a positive value of volts, the battery works, right? So positive E means the cell is thermodynamically favored or spontaneous. So when we have a G that's negative, we have an E that's positive. And we have a G that's positive, we're going to have a voltage that is negative. So we'll talk more about that later, but that kind of makes sense. And I think it's easy to remember a positive voltage on a battery means it works, right? So it means it's spontaneous. So you can remember a positive E means it's a spontaneous or delta G is negative. So in this first problem, we're just going to start now working through some stuff for practice. Nothing really else new today other than the calculation of K. So part A of number 30 says find the free energy of the reaction at 25 degrees Celsius. And they actually say 25, right? So good news for us is we can just straight up use Big Mama. We don't even have to use Ghetto Homies because we're at 25 degrees and it's faster. We just have to do the math once. So our free energy, delta G, is equal to products 2 times 51.31 minus 1 times 97.891. And when we do that math, we get a delta G of 4.73 kilojoules per mole. Now I'm looking down and I see the next problem is asking me to calculate K. So I know I have to use this equation, fondly coined as negative rat link. And I have a little rat link on the board or above the board with my little figures that you can look at in class. But because of that R, which is the energy R of 8.31 joules per mole Kelvin, we have to be in joules. So I'm going to go ahead knowing that's coming and convert this to 4,730 joules per mole, which is going to be a nice little thing. So now when I go and calculate K, delta G is equal to negative RT ln of K. My delta G is 4,730 joules per mole K. That's equal to negative 8.31 joules per mole. And this is joules per mole. I don't know why I wrote K there. Joules per mole. This is joules per mole K times the temperature of 298. And we're solving for the natural log of K. So let's talk about solving here. We have a lot of students who struggle on the AP when I grade these of solving for that K because they don't know how to use their LN button. This is not LOG, this is LN. So when you take this, I would divide by, remember this is negative that and that, you get a number that is equal to natural log of k, and then you take that number and go e to that number to actually solve for the k. So I need you to stop the video and practice it and see what you get. So when I actually get k, my value is 0.148. Now let's talk about that. Does that number make sense? We have a k that's less than 1. So it means the reverse reaction is favored, meaning the forward reaction is not favored. Is that true based on this value? Yep, our delta G is positive, so that means our k has to be less than 1. So this checks out as being a k that makes sense. Please do that logic when you're solving problems because it'll save you from making silly math errors. Okay, next problem. Consider the reaction and provided data. They give us a reaction. Oh, they snuck in a little heat here, meaning what? It's endothermic. That's a little something we're going to be using. And then it gives us delta H and delta S values. Part A says the Kc for this reaction at 750, so the Kc, I'm just going to jot this down, at 750 is equal to 1.12 times 10 to the third. Using no math, just logic, what would you expect the value of K? Would you expect the value of K to increase or decrease at 300? So look, this is at a lower temperature than 750, right? So we're saying we're taking away heat. Think about Le Chatelier's principle. We take away heat. We're taking away driving force. And I know this should have a double-headed arrow. I'm like, where's the double-headed arrow? So if we remove heat, we know the reaction is going to shift left. So as heat goes down, so we remove heat, temp decreases, and that is a left shift. Okay, I think everyone's hopefully on the same page. What happens to the magnitude of K, though, when we shift left? Left shift, we get more what? Remember, it's products over reactants. If we shift left, we get more reactants. So the magnitude of K decreases, right? So we're going to predict, based on our logic, that when we go to 300K, our K is going to get smaller. K will get smaller, hopefully. So now we get to math it up and prove that. So the first thing they're asking us to do, they're leading us through the calculation, and the first thing they're asking us to do is to find our delta H. So I'm going to make this bigger so I can write bigger and then shrink it again. So usually you can't see the tables on my screen, but you can see it on your notes. I'm going to do Big Mama to find delta H. So delta H is equal to products minus reactants 4 times negative 92.307 minus 2 times negative 241.818. And that's equal to 114.408, and this is kilojoules. Now, I know I'm going to have to solve for K at some point, so I know I'm going to have to use negative rat link, so I know I'm going to have to be in joules. So I'm just going to go ahead and immediately convert this to 114,408 joules per mole. All right, so that is my delta H. So now let's solve for delta S. Delta S is equal to 4 times 186.98 minus, we've got two products there, don't we, that aren't free energy. So I need to make sure to do a plus there. 1 times 205.138. All right, those are my products, minus reactants. Oh, we got two reactants too. It's a long problem. 2 times 233.066 plus 2 times 188.0 835. Yay. All right. That's a lot of math. So go ahead and plug that into your calculator. If you need to stop the video, do so. And then my delta S value is equal to 108.988 joules per mole K. All right, so now I have both of those values. Shrink this guy back up. Next part of the question says, I'm going to really shrink this up. Calculate delta G. So now we're going to plug that stuff into get homies, right? So delta G is equal to delta H minus T delta S. So when I do that, I get delta G is equal to 1144. That is messy. Try that again. 114408. And we're finding delta G, it says at 300. So 300K times my S of 108.988. And remember, this is going to be in joules when I'm done. So I get my delta G of 81,712 joules per mole. K. Oh, not K, just joules per mole. All right, so that's my delta G. Now I have to calculate K for the reaction at 300. So I use my G, I'm going to use negative Ratlink. Delta G is equal to negative Rat, and I already have that at 300, and I'm finding the K at 300, so that was the whole reason I used 300. So I have 81,712. This is why we had to convert to joules, not kilojoules, because of right here, negative 8.31 joules per mole K. Blunk, blunk, times 300 times ln of K. All right, so when you do your fancy maths, K ends up being 5.83 times 10 to the negative fifth. All right, so our Kc at 300 is 5.83 times 10 to the negative fifth. Did it decrease as we predicted? Yay, it did, right? We said that K would get smaller as temperature dropped. Temperature dropped, K got a lot smaller. So it looks like we are logical people. That's awesome. Number 32 is another long problem, multi-part thermo problem that takes all your knowledge of thermo and puts it together. So we have a problem. If you look, they give us a reaction. You've got to see that they give us K there. That's important. Then they give us a data table with H and S and G. And then it says calculate delta G for the reaction using only the provided information. Well, if you look, I don't have the delta G of water. And I can't use ghetto homies because if you look at the table, they don't give me anything about HOCl, HOCl. So hypochlorous acid, so I'm like, oh my God, what am I supposed to do? How am I supposed to find G? I don't have enough information. Well, it turns out you do, because look, you have K. So we can use Ratlink. Be sure to look for that. They sneak that in and people are like, I can't solve, or they try to make up numbers for HOCl, and it's a big mess. So all we're going to do is plug into this. So delta G then is equal to negative 8.31 times the temperature, 298, times natural log of 0.090. And when you solve for this, you get a delta G of 5960. Please don't forget that it's joules per mole, not kilojoules. Okay, awesome. Now we have that to go from, but we're not going to use it necessarily right this second, but just know we now know delta G of the above reaction. Delta G, check. So now it asks us to find the delta H, but here they're saying use the table below. So they're having us use bond energy. So do we remember what we do when we have bond energy? To find delta H, it's bonds broken minus bonds formed. So let's take a look at what we're breaking. So I'm just going to rewrite the reaction here. H2O plus Cl2O gives you 2 HOCls. So we know H2O kind of looks like this, right? So we're going to have to break 2 OH minuses. And to that we add Cl2O, same thing, ClOCl. We're going to break 2 OCls. So those are bonds broken, minus, what bonds are we forming? We're forming an HO and a ClO, but 2 of them, so we do 2 HOs and 2 OCls. Aren't we doing the same thing then? Aren't we making the same that we're breaking? 2 OHs, 2 OHs. I'm going to change the color. 2 OHs, 2 OHs, right? Those kind of cancel out. 2 OCls, 2 OCls. Wow. So our delta H is actually 0. 0 joules or kilojoules? Ha, doesn't really matter. It'll be both. Okay, so I'll just go ahead and write joules. 0 joules per mole. Does everyone get that? We're breaking and making the exact same bonds, so no change in enthalpy. Okay, let's move on to the next slide. Part C. So because I can't see the other slide, I'm just going to write the results from what we've already determined. In Part A, we determined that our delta G was 5960 joules per mole by using RATLink. And in Part B, using bonds broken minus bonds formed, we determined that delta H was 0 joules per mole. So that was good. Now I'm going to go back and look at the question. It says find delta S. Well, again, we don't have any HOCl in that table on the previous page, but now that we have G and H, we can use ghetto homies. So they don't really talk much about a temperature, so I'm going to assume 298. I've got 5960 joules per mole is equal to 0 minus the temperature of 298 times the delta S. So I can solve, and when I solve, I get a delta S of negative 20 joules per mole. Okay, so here's the fun part. They want us now, remember how we couldn't do anything with that table because they didn't stupid give us HOCl information? Well, now they actually want us to find the H and the S of that information. So this is what's interesting. So what that equation was, I'm going to change colors actually, make it stand out a little bit. The reaction, I'm just going to write it down again so we can see it, was water plus Cl2O makes 2 HOCls. So if you recall, we have a delta H now and a delta S for that reaction. So we have the delta H and delta S for that reaction. So what we can do is use Big Mama putting an X in for the HOCl for both the delta H and delta S and set it equal to the previously calculated delta H and delta S values. So we're going to go ahead. We have to do one at a time. Let's start with delta H because they asked for that first. Delta H, I'm going to set this equal to 0 because that's what we figured out the delta H of the reaction was, is equal to 2 times X, because we don't know HOCl's heat of formation, minus 1 times negative 242 plus 1 times 80.3. And then I can solve for my overall delta H. Again, if you need to stop the video and do the calc yourself first to check the heat then of just that X when I rearrange and solve. Remember, we're solving for that X. I got negative 80.6 kilojoules per mole. Okay, so now we have to do the same to find the S. So I'm just going to draw a line here so we don't get all my numbers confused. And we're going to solve for the S of HOCl by, again, setting it equal to what we just calculated right there. Negative 20 is equal to 2 times x minus 1 times positive 266.1 plus 1 times 189. And my delta S ends up being of HOCl ends up being 218 joules per mole. Okay, and the last part, part E here, is asking for us to find the K at 300. Well, can't find the K at 300 unless I know the G at 300. So I'm going to use ghetto homies and again utilize information that I've already solved for. Delta G we have was not for 300, it was for 298. So H is 0 because H and S aren't temperature dependent, times 300 K times negative 20 joules per mole. That gives me a delta G of 6,000. And again, that's at 300. So now I can use RATLink and solve 6,000 is equal to negative, and this is again joules per mole, is 8.31 joules per mole Kelvin times the temperature of 300 natural log of K. So when I do my manipulation and I solve for it all, I get a K equal to 0.0901. I hope your answer matches mine. And now we're going to start, last long problem. These are cumbersome, but this is how they show up. A little bit of the kitchen sink, everything, what's that saying? Everything but the kitchen sink. Well, I think these problems have the kitchen sink in them too because there's so much stuff. So in this problem, it says the enthalpy of combustion for heat of combustion for oxalic acid is 246.02 kilojoules per mole. And it gives you a bunch of stuff. And notice, look at how convenient. The heat of formation of oxalic acid is missing. So you can bet your bottom dollar we're going to have to solve for that. But let's just start the problem. Part A says write the balanced chemical equation that describes the combustion of 1 mole of oxalic acid. Well, that's easy. So we're going to combust 1 mole. So oxalic acid, H2C2O4, is going to, that plus sign is so ugly. Oh, it's a 4. See, I didn't even know it was a 4. I thought it was a plus. O2, and we know that whenever we combust, we make CO2 plus H2O. Now we need to balance this. So we have 2 C's, 2 C's, 2 H's. I'm going to leave that alone. That gives me 5 oxygens, right? Is that correct? Yes. Here I have 4 oxygens, and I only need 1 of these 2, so I'm going to put a half there. That is a balanced reaction. Now, one thing I want you to make the connection with is that if you look at the stem of the problem, did you see that it had the heat of combustion for oxalic acid, the value up there? That is the value for this reaction. This is a heat of combustion reaction. So the delta H for this reaction is that 246.02. And that's going to be something that you have got to be able to connect. Part B says write a balanced chemical equation describing the standard heat of formation. So heat of formation is forming 1 mole. We're going to form 1 mole of oxalic acid from its elements. So we have 2 H's, H2, 2 C's, that's not a diatomic, and we have oxygen, 4 of them, so we need 2 O2s, and that is a heat of formation reaction. Using the information given above in part A, calculate the delta H of formation of oxalic acid. See, I knew that was going to happen. Well, how do we do that? This is the key. We know that this reaction, Big Mama style, is equal to that value, and this is going to then be our unknown, like we did in a previous problem. So we're going to set Big Mama equal to 24602. 246.02 is equal to products minus reactants, 2 times -3. Everything else is in the table. So we're able to solve, and this is going to be in kilojoules, products minus 1x. Yay. And when we solve for our x, you can stop the video and solve on your own. The heat of formation of the oxalic acid is equal to, I got -1319 kilojoules per mole. So that's what we'd put in the table here, -1319. Thanks. Thanks for, they could have just given it to us and made our life a little bit easier, but of course not. Okay, let's look at part D then. Part D says calculate the heat of the delta S of formation of oxalic acid. Well, we're going to just use the delta S on the equation in B. In other words, we're going to use all the delta S values from the table and set Big Mama equal to them and solve. And again, you might be asking, well, why don't we use the A equation? Why do we use B? We use B because B has to have, B is by definition formation. Remember, B is a formation equation. So that's the equation we have to use when we're setting up to solve for our delta S. Delta S then, I really want to change colors. Delta S then is equal to 1 times, and I'm getting all those delta S values from the table, minus 1 times 130.6 plus 2 times 5.69 plus 2 times 205.13. When I solve my delta S, you can stop the video if you want, is -435. Nope, it's not. It's -432 joules per mole Kelvin. Okay, so recap for part C, we used the heat of combustion equation because we knew the value to set the reaction equal to. In part D, we had to use the heat of formation equation because it wanted us to find the heat of formation of the actual delta S of that formation reaction. Okay, and now we're going to find the delta G of formation. So from part C, we can easily get our delta H of formation because it was calculated. So we're going to use ghetto homies for this. And we're going to get our value of delta H from part C minus 298 times, we're going to take our part D value and convert it to kilojoules. That is the delta S we literally just calculated. And so our delta G is equal to -1190 kilojoules per mole. And the last question, this is again the amount of heat or free energy associated with forming 1 mole of oxalic acid from its elements. Is the formation of oxalic acid from its elements spontaneous? Yes. And why? Because our delta G is negative. And just a reminder, you won't be asked if it's spontaneous, you'll be asked if it is thermodynamically favored. And the answer would be yes, because delta G is negative. Yay, that is it for the crazy problem solving. So let's just recap, and this is something that we talked about in equilibrium, relating the K to endo or exothermicity. So if we look at both of these graphs, the first instruction is to label the graph endo or exo. So in this first graph, we have super high reactants, low products. Where did the energy go? Out, so this one is exo. And in this one, we have low reactants, high products. Where did the products get the energy to make that happen? It came in, so this is endo. And then the next question is, how does knowing if a reaction is exo or endothermic, how does it relate to the magnitude of K? Well, this has to do with that running the hill, right? If you look at your exothermic reaction, an exothermic reaction, the forward reaction is favored because the forward activation energy is a lot less than the reverse activation energy. I'd rather run the forward hill than the reverse hill. So in exothermic, the forward is favored. And if the forward is favored, we know the magnitude of K is greater than 1. In an endothermic process, we know the opposite is true. In an endothermic process, I would rather run the reverse hill because its activation energy, that hill is a lot lower than the activation energy of the reverse. So in an endo, reverse is favored. Therefore, K is less than 1. And that's all pretty much review, I hope. Hope you remember that because we did do that in equilibrium. And that, my friends, is the unit. So we're going to be spending a few days practicing, but that's it. So if you have questions, come and ask your teacher. And let's get ready for your group quizzing and your AP extra credit and your test.